So welcome to the next unit, moving on from crude oil, hydrocarbons, because of course a large number of the products of the fractional distillation of crude oil are hydrocarbons, in particular two types, alkenes and alkanes, which we will be looking at, which involve primarily two atoms that make the molecules, carbon and hydrogen. So these are the learning objectives for this topic. Okay, there are quite a number of them, but they kind of interrelate with each other. We're going to define some terms, know what hydrocarbons are, understand how to show organic molecules like the hydrocarbons in different ways, know what is meant again by a series of number of terms, how to write possible structure and displayed formula, so we'll learn what those terms actually mean, recall the general formulas of the alkenes and alkanes, and again focusing on displayed formula for the alkenes and alkanes, and describe a number of different reactions that the hydrocarbons can undergo. So first, let's welcome us to a new family, the family being the alkanes. Now, the alkanes are the simplest family of hydrocarbons. And hydrocarbons are compounds that contain hydrogen and carbon only. Many of the alkanes, as we discussed in the last topic, are used as fuels, and methane is a major component of natural gas. Ethane and propane are also present in small quantities of natural gas, and they're also alkanes, and they're important constituents of liquefied petroleum gas, or LPG, and this comes from the crude oil distillation we discussed in the last topic. So we're now just going to go through the series of the alkanes. Okay, so the important term here is the homologous series. A homologous series is a series of compounds like the alkanes which have the same functional group. Okay. Alkanes don't really have a functional group, but as we move on to the alkenes, you'll see that they have a functional group. They have similar chemical properties due to the fact that they have similar structures. They show a trend in physical properties and can be described by the same general formula, which for alkanes and alkenes we'll learn about more. And they differ from the next by just a CH2 unit, or a methylene unit. Okay, the alkanes are the simplest homologous series. Hence, we're starting with them, and they don't really have a functional group, as already mentioned, but they just contain these carbon-carbon and carbon-hydrogen single bonds, which is essentially the basis for all organic compounds. Okay, so let's now look at the homologous series. You only have to know the first 6, okay, and we'll also be looking at some terms. Okay, so the first alkane is methane, contains 1 carbon and 4 hydrogens. Now this CH4 is known as the molecular formula. It basically tells you the number of carbons and number of hydrogens, well, basically the number of atoms in a molecule. Okay, so methane contains 1 carbon and 4 hydrogens. That's known as the molecular formula. And as previously discussed, it's the main constituent of natural gas. And this is known as its displayed formula. So this is, if you're asked to draw a displayed formula, it's basically showing the bonds between each of the atoms. So hydrogen can form 1 single bond, carbon can form 4. So that's how you would display the structure of methane. So the next one is ethane, also used in natural gas. It has a structural formula of C2, a molecular formula of C2H6, and also now a structural formula. So the structural formula just tells you how the atoms are arranged. Okay, so that's another type of formula that you have to get used to. Okay, and that is the displayed formula of ethane. Alkane in the homologous series is propane, okay, which has the following molecular formula, the following structural formula, and the following displayed formula. And it's used also as a fuel, probably in the gas for barbecues. So then the 4-carbon alkane is butane. C4H10 is its molecular formula. The structural formula being CH3, CH2, CH2, CH3, and that's its displayed formula. Then again, it's used as a fuel. Okay. And the fifth one you have to know, because you have to know 6. Next one is pentane. C5H12 is its molecular formula, and its structural formula is CH3, CH2, 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 CH3. Notice there's a CH2 being added on each time. Okay, and that's the displayed formula, and again it's used for a fuel. And the last one is hexane, which is more of a solvent. Okay, just like water would be a solvent, hexane is a solvent as well. C6H14 is a molecular formula, and that is getting rather long structural formula, and that's this displayed formula there. Okay, so you can probably start to work out the relationship between the number of carbons and number of hydrogens. Okay, and this here is known as the general formula. So the general formula for the alkanes is CnH2n plus 2, where n is the number of carbons. So for example, if there's 3 carbons, then there are 2 times 3 plus 2, 8 hydrogens. So the formula for propane, C3H8. If you want to work out the formula of an alkane with 15 carbons, you could work that out as being C15H32, and so on. The reason that alkanes and other homologous series can be described by general formula is that each member differs from the next by this CH2 methylene unit, just by adding it on. Okay, so there we go. Those are the ones that we know. And I've also thrown in octane, which is also a fuel, just to add a bit of depth. Okay, so they're all part of the homologous group that is the alkanes, because they have similar chemical properties. They can bust, okay, form fuel as a fuel, to form carbon dioxide and oxygen, and they have similar structure and functional groups, so CH and CC single bonds. And they're generally unreactive, but as I've said, because they're fuels, they burn exothermically, and the longer chains burn less easily. So methane is very explosive. Octane requires a bit more ignition to get going. Okay, so the first 4 alkanes are gases at room temperature, and all the other alkanes you're likely to see in IGCSE are liquids. Solids start to appear about the C18 mark. The molecules of the members of the homologous series increase in size in a regular way, so the boiling points increase as you go from methane down to octane. This is because as the molecules become bigger, the strength of the intermolecular forces of attraction between them increases. This means that there's more energy required to break these bonds between the molecules, and this means that it's more energy required to make them change phase from, say, liquid to gas. Okay. So because the chemical properties are dependent on the functional groups and bonding between the molecules, because the alkanes can only contain these carbon-hydrogen single bonds, they're all going to behave the same way. That's why they're fairly unreactive. Okay. So then we look at the idea, the final type of a formula we have to learn, which will be more helpful for next year when we use it, is the empirical formula. Okay, so the empirical formula is the smallest ratio of elements in a molecule compared to the molecular formula, which gives a total number of elements present in one molecule of the compound. So for example, the molecular formula of, say, decanane, okay, C10H22, you can divide those numbers by 2 so to get a clear ratio. So the ratio is actually C5 to H11. So it's basically the empirical formula. Okay, another example could be H2O2, okay, hydrogen peroxide, that's the molecular formula, but the empirical formula is simply HO because you can divide both sides by 2. So it's basically the simplest ratio of the molecular formula. That's pretty much all the formulae you have to know for this unit. Okay, Another important difference when we look into alkenes as well is that alkanes can be considered saturated compounds. So what does that mean? Well, it means they don't have any double bonds. Okay, carbon forms basically 4 single bonds. Okay, no double bonds means it's saturated. They'll become more important when we look at unsaturated compounds like the alkenes, which are next. Okay, and another important aspect is isomers. So isomers have the same formula but different structures. They're called structural isomers. So here we have 1, 2, 3, 4 carbons here. So this is known as simply N-butane. Okay, and basically because an isomer is a compound which has the same molecular formula but different structural formulas, you can have straight chain alkanes, which is the one that we've looked at because basically the carbons all form a straight chain, or they can have a branching chain. Okay, and the example here is going to be this one here. So this is known as 2-methyl propane. Okay, because the carbon is on the second, and this is known as a methyl group, CH3. Now you don't have to know this in detail. All you have to know is that structural isomers can exist. Naming them isn't critical this year or next year, more when you get into IB or A level. So basically alkanes can react in 2 ways. Okay, they can react with a halide like chlorine or bromine to form an alkyl halide. Okay, and the other way they can react is through combustion. Okay, reacting with oxygen to form carbon dioxide and water. Okay, that's the incomplete complete combustion we discussed in the last topic. So focusing on the reaction of alkanes with halides, chlorine or bromine. So alkanes form chloroalkanes only when there's UV light about. Okay, so if you did it in the dark, this reaction wouldn't happen. And it happens in a chain reaction. The details you don't have to know about. You just have to know that alkanes react with bromine and chlorine to form bromo and chloroalkanes in the presence of UV light. Okay, and the mechanism isn't important. But basically, the product can be attacked further by these things called free radicals until all the hydrogens are replaced. And because they're replaced, they're being substituted. So these reactions are called substitution reactions. In this particular example, chlorine substitutes for hydrogen. Other examples, bromine can substitute for hydrogen. And it makes a clear solution and colorless solution at the end. So essentially, this is the example for chlorine, but the associated bromine reaction can happen. So if you add a mixture of methane with chlorine or bromine gas, it'll be greeny orange. Okay, it'll be green if it's chlorine, orange if it's bromine, because you've got this presence of a chlorine or bromine. If it's exposed to sunlight, the reaction mixture will lose its color. Okay. And you can have either monosubstitution, which is this example here, okay, or disubstitution, trisubstitution, or tetrasubstitution, because the reaction continues going, okay. So, because when the propane reacts with the halogen, it's possible to form 2 organic products even when only monosubstitution occurs. The products are structural isomers of each other. They have the same molecular formula but different structural formula, okay. So when bromine or chlorine reacts with propane, we get both 1 chloro or bromo propane or 2 chloro or bromo propane. So that's pretty much an example of the substitution reaction. Okay, so then we can move on to the next group of homologous series, the alkenes, another family. Okay, so these are the alkenes as opposed to the alkanes. You'll notice the difference. it is the double bond, okay, and there's no longer an ane, okay, we end now with an ene, okay, they're no longer the alkanes, they're the alkenes, okay, and the alkenes are an homologous series of hydrocarbons which contain a carbon-carbon double bond. The C double bond C bond is a functional group, okay, so remember we discussed functional groups in the last part of the topic, okay, that's known as a functional group because all alkenes have a carbon-carbon double bond. And you only have to know the first four. Okay. Ethene, of course, can't have methane because you need a carbon-carbon double bond. You can have ethene, propene, or butene. And notice here that the carbon double bond can either be on the first carbon or the second carbon. So these, of course, are isomers of each other. Okay, structural isomers. Now the difference between this functional group and the alkanes is that the alkenes are unsaturated compounds because they contain a carbon-carbon double bond. A saturated compound only contains the carbon-carbon single bonds. Okay, they have very similar properties to the alkanes, and they tend to be gases up to C4H8, and the next dozen or so are liquids. Okay, so as I discussed, they're unsaturated, they contain a double bond, they're slightly more reactive due to the fact they have this electron-rich double bond, and they can now not only substitute reaction atoms, they can add reactions known as an addition reaction. So alkenes can also undergo combustion reactions like alkanes, forming carbon dioxide and water. So for example, you can have C2H4, which is a gas, okay, ethene, plus 3 oxygen, which of course is a gas, and that can react to form 2 CO2 gas plus 2 liquid. Okay, that's combustion, one kind of reaction. But the other reaction is, of course, the addition reaction, which we're looking at in more detail in the next slide. Okay, so it's going to be basically the alkene reacting with a halogen to form a colorless product. So the addition reaction, this is basically the test for alkenes. So the carbon-carbon double bond is a functional group. The functional group determines the chemical properties of the compound, and because of this, alkenes are more reactive than alkanes because there's more electron-rich double bond. So alkenes undergo addition reactions, and part of a double bond breaks to become a single carbon-carbon double bond, and the electrons are used to join other atoms onto the adjacent carbon atoms. So the example we'll use here is the test between alkenes and alkanes and the reasoning behind that. So if you have an alkane and you react with bromine water, then you're going to have a purple color, okay, because chances are there's no UV light around, okay, there's going to be no reaction, it's going to be very slow, whereas an alkene is going to react with the bromine to form this dibromo compound, which is colorless, okay. So the test is basically you add bromine water to an alkane, you'll see no reaction. You add it to an alkene, you'll get decolorization. And we're going to look at the reasons behind that as we go on. Okay, so bromine adds to alkenes without any need of heat, light, or catalyst. Okay, there's no need for UV in this example. The reaction is often carried out using bromine water, which is basically bromine dissolved in water. And what happens is, like in the previous slide, the bromine water is orange, but the product itself is going to be colorless. And basically this is the equation here. Ethene plus bromine, which is kind of yellowy orange, reacts to form dibromoethane, which is colorless. Okay, so this here is basically what happens here. So this is the reaction for the alkene, and this is the reaction for an alkane. Okay, so the alkene makes a product which is colorless. Okay, so that means the solution goes colorless, whereas these guys, they're going to have extra bromine floating about, so that's going to be orange because you've still got bromine floating about. Okay, so it's a good way to test if you have a alkane or an alkene. So any compound with a carbon-carbon double bond react with bromine in a similar way to this. Okay, if you shake an unknown organic compound with bromine water and it goes decolorized, you know you have a carbon-carbon double bond. Okay, so the organic layer containing the alkene is on top usually, and you'll see that the bromine water has going to be completely discolorized, showing the presence of a carbon-carbon double bond. Whereas a tube containing an alkane, basically the color of the bromine will still be there. The alkanes do not decolorize the bromine water because they do not contain a carbon-carbon double bond. Okay. Just to finish up, just to kind of link everything together with the crude oil topic, we'll look at a bit of cracking. So what happens is that crude oil contains too many long and not so useful molecules. Okay, but we can break these long molecules down into shorter ones by a process known as cracking. The long molecules are passed over hot broken ceramics and split up into smaller molecules, and you use a catalyst called aluminium oxide. Okay, and you'll notice that the double bonds have formed, so you've actually gone from an alkane to an alkene. Smaller sized alkenes, but still more useful. Okay, so cracking an alkene product produces a range of smaller alkanes and smaller alkenes. So just to finish up, we will look at a summary video from the virtual school on alkanes and alkenes.
In this video, you will learn about the homologous series of the alkanes and alkenes and their structure. Before we look at the structure of these molecules, you may wish to recap your understanding of bonding by watching our covalent bonding video. Alkanes are saturated hydrocarbons, meaning they contain only single covalent bonds between carbon atoms. A single covalent bond is a shared pair of electrons. Let us take our first alkane in the series, methane, CH4. Carbon has 6 electrons in total, 4 of these being in the outer shell. Carbon, therefore, always needs 4 more covalent bonds to be stable. In methane, the 4 hydrogen atoms have only 1 electron and so covalently bond to the carbon atom, each sharing a pair of electrons. Methane is known as natural gas and is often used as a fuel in homes for heating and cooking. It is also the gas released by cows by belching and flatulence, as it is produced by the fermentation of food by bacteria in their stomachs. The next molecule in the homologous series of alkanes is ethane with 2 carbon atoms. As you can see, a single covalent bond is formed between the 2 carbon atoms, with 6 more hydrogen atoms covalently bonded to complete the molecule. Now we understand the way these molecules are bonded, we can show the next molecule in displayed formula, representing the covalent bonds simply with lines. Here is propane, followed by butane. This alkane series continues and follows the general formula CnH2n plus 2. A general formula allows us to describe a series of molecules that differ from each other by a constant unit. Let us look again at ethane. Using the formula CnH2n plus 2, where N represents 2 for the 2 carbon atoms in ethane, we can see that the number of hydrogens will be 2 multiplied by 2 equals 4, plus 2 equals 6. So 6 hydrogens, C2H6. Using this, we can find the molecular formula of other alkanes. For example, decane, an alkane with 10 carbons. Pause the video now and use the general formula to work out the structure of decane. You should have got the answer C10H22, where N equals 10 for the 10 carbons. Therefore, 10 multiplied by 2 equals 20, plus 2 equals 22. 22 hydrogens. Let us look now at the homologous series of the alkenes. These are unsaturated and so contain a double covalent bond between two carbon atoms. Here is ethene. Since there is a double bond, there are now two shared pair of electrons between the two carbon atoms. Each carbon atom now has only 2 electrons which covalently bond with a total of 4 hydrogen atoms, 2 on each carbon, to complete the ethene molecule. You are only likely to come across alkene molecules with just one double bond, although there can be more within a molecule. The next molecule in the series is propene. As before, there is a double covalent bond between 2 of the carbon atoms, but the other is just a single bond. We now need to fill the molecule with hydrogen atoms to ensure that each carbon has a total of 4 bonds. 2 hydrogen atoms are required at this end of the molecule. This middle carbon already has 3 bonds and so requires just 1 hydrogen, and at this end carbon has only 1 bond and therefore needs 3 more hydrogens. Since we now understand the covalent bonding in these molecules, let us replace the dot-cross diagram with the structural formula. Here is the structural formula of propane. Pause the video now and try and complete this structural formula of butene. Here is the completed structure. Did you get it right? Here are the structural formulas of the first 4 alkenes. Pause the video again and try and complete the general formula. What is the relationship between the number of carbons and the number of hydrogens? Hopefully you got the structure CnH2n. Quite simply, there is double the number of hydrogens than the number of carbons. So, as an example for decane, the molecular formula would be C10H20. Now, at the end of this tutorial, you should have a better understanding of the bonding in the alkanes and alkenes and how each homologous series follows the pattern given by its general formula.